Hello, welcome all of you in the fourth lecture of bioprocess engineering. I hope you all are fine and staying at your home, taking good care of yourself, family, neighbors, and those who are in need. So today I'm going to discuss the fed batch operation of a mixed bioreactor with you all. As in the older lectures, we have seen the operation of a batch reactor. In upcoming lectures, we will see how the fed batch is operated, what is the kinetics associated with the fed batch bioreactor, right? So, fed batch operation, coming straight to the point, fed batch operation of a mixed bioreactor. Hopefully, it is visible to you all. What is a fed batch? Fed batch as a type of process, fed batch is a type of process in which we add the substrate or the medium at regular interval of time. So basically, it is a kind of batch process that we operate in a manner where we continuously supply the nutrient to the reactor. Like in the batch, you start by putting the medium inoculum, right? And you withdraw the exhausted medium, the cells, and the product at the end of the process. Here also you will add up the medium, you will add up the inoculum in the beginning, you will start your process, but after certain time period you are going to feed the reactor with a fresh supply of the medium, right? And this you are going to do intermittently, right, throughout the process. And again you will withdraw the products, the exhausted medium or the used medium and the cells at the end of the process only. So let's first see the flow sheet diagram for the same. What is this symbol? This is rotating, right? So mixing is taking place inside the reactor. So here we have a feed stream. What is there in the feed stream? There is feed flow rate, right? There is sub biomass, substrate, and the product. What is there inside? The total volume, cells, substrate, and product. So here we will see what are these terms. The volumetric flow rate. Volumetric flow rate, F. We can see that, right? And Xi is the concentration of cells in the feed which is coming in. The Si is the substrate concentration in the feed, and the Pi is the product concentration in the feed. These are the terms. V is the total volume, X is the X is the biomass concentration inside the reactors, S is the substrate concentration inside the reactor, and P is the product which is synthesized inside the reactor. Here what we are going to assume? We are going to assume that the feed flow rate F is constant. If F is constant, which means that the liquid volume will keep rising. So here F is constant, V will increase with time. Why volume will increase? Because it is a fed batch process. You are continuously adding up the medium. You are not removing or withdrawing anything. So the reactor volume will keep rising till the end of the process, right? So our assumption is the feed flow rate, the rate at which the feed is being supplied inside the reactor is constant, and the volume is keep changing with the time, right? So for the fed batch operation, for fed batch, unsteady state mass balance equation is used, right? So for the fed batch, we are going to use unsteady state mass balance equation, right? So what is that equation? Let's see. D rho V upon dt equals to Fi rho I minus Fo rho O. What are these terms? We can see the rho is the density, right? Fi is the feed flow rate of the input stream, rho I is the density of the input stream. Similarly, Fo is the feed flow rate of the output stream, and rho O is the density of the output stream, right? So these terms are clear. This is rho I and rho O are the densities of the input and output stream. Fi and Fo are the feed flow rates of the input and output streams, and rho is the density of the reactor content. V is the total liquid volume, right? Now just see the flow sheet. What is visible over there from the flow sheet? It is very clear. It is very clear that Fo equals to 0. Why? Is there any output stream? No. No output stream is there, only input stream is there. So obviously this Fo equals to 0, right? And this rho this Fi is equals to F. Why? Why the feed flow rate of the input stream is equal to the feed flow rate or the F? Why? Because we have assumed that F is constant. So the feed flow rate of the input stream, feed is being supplied at a constant rate. So there will be no difference in the Fi and F, right? So Fi will be equals to F. Fine. And here also we in case of many bioprocess engineering operations, we normally use a dilute medium for the growth and cultivation, right? That dilute medium has many mass transfer and heat transfer significances that we can see later on. So here we are supplying and we are supplying a dilute medium, right? So again we have so if, excuse me, if rho I is equals to rho, why I am saying, because we are supplying a dilute medium whose density is constant. So the density, if density is constant, then the density of the input stream will be equals to what? Rho, right? And your rho O will be equals to 0. This is 0 because again there is no output stream. So the density of the output stream will be equals to 0. If we put all this in this particular equation, let's see. We can write, if density is constant, we can take it as out of the differential, so we can write it as rho dv by dt equals to what? Fi is equals to f, rho I is equals to rho minus what? Rho o is equals to 0, fo is equals to 0, so this term will be 0, right? So what we are going to have? We are going to have dv by dt is equals to f. This much we are going to get, because we will cancel this row with this one, right? So here we have got a very important conclusion, and that is what? Dv by dt equals to f. This we are going to use in the further applications, right? So let us now focus on the mass balance on cells, right? So let us apply mass balance on cells. We know that particular equation here, right? dm by dt equals to what? mi hat mo hat plus rate of generation minus rate of consumption. Now we are performing the mass balance on cells. So what I mean on X, that is biomass concentration, right? So let us find out the values of the different terms that we are going to use here, right? So M, the mass of the cells. What will be the mass of cells? Mass of cells will be equals to cell concentration multiplied by the liquid volume. We have seen this in the batch as well. What will be the mi? Mi hat will be equals to what? Feed flow rate, that is F multiplied by biomass concentration in the feed stream or the input stream, right? And what is this MO? MO hat will be equals to 0, because there is no output stream. बाहर कुछ भी नहीं निकल रहा है. What will be the rate of generation? Rate of generation, cells are being multiplied, the number is increasing, biomass is increasing, so the rate of generation of the cells will be equals to what? Volumetric rate of cell growth multiplied by the reactor volume, the liquid volume. So we'll have mu x v. Rx is equals to mu x and v, right? What will be the rate of consumption? Rc will be equals to, there is a certain amount of cell death that is taking place inside the reactor. So we have volumetric rate of cell death into the reactor volume. So this Rc, further Rc will be equals to, Rd is equals to kdx. So into V. So now you have all these terms. Now we can simply put all these terms in this general equation. Let us see how we are going to do it. So dm, what is m? X into V upon dt equals to, what is mi? Mi is equals to fxi minus, what is mo? Mo is 0, so I am not considering that. I am directly coming to this, plus rg. What is rg? This is mu x v minus, what is rc? This is kd x v. This we are having, right? So dxv upon dt equals to what we are having? fxi minus, no, plus, we can take the xv as common, So what we have, mu minus kd out of the bracket xv, right? This is what we are having. Let's further see what is going to happen. Let's see. So this is the equation that we have got. The problem is that here the volume is not constant, it is changing, right? So if volume is changing, then what we can do, we have to expand this differential. We have to expand this differential by using the product rule. So as per the product rule, I am going to expand this particular differential, that is dxv upon dt. So I can write it as x dv by dt plus v dx by dt. This is simply the product rule for the expansion of the differential equation. So here we have fxi plus mu minus kd x into v, right? So what we have, dv by dt, we have dv by dt equals to f, right? So we can write it as xf plus v dx by dt equals to fxi plus mu minus kd x into v, right? So let us now divide the whole equation by v, dividing both sides by v. So what will happen? X f by v plus this v and v will get cancelled out. So we have dx by dt equals to f by vxi plus this v, and when you divide the v it will get cancelled out. So you have mu minus kd out of the bracket x. This